For most of the last decade, hardware design followed a familiar rule. Devices were built to run apps, display content, and connect reliably to the cloud. Intelligence lived elsewhere. Phones, laptops, wearables, and smart devices acted mainly as access points to remote computing power. In 2026, that assumption no longer holds. On-device AI has become a core design requirement, and it is fundamentally reshaping how hardware is designed across the US tech industry. This shift is not about adding one more feature. It is about changing the internal priorities of hardware engineering. When AI runs continuously on the device itself, everything from chip architecture to thermal design must change. Hardware is no longer optimized just for peak performance during active use. It is optimized for constant background intelligence. One of the most visible changes is the rise of dedicated AI processors. Traditional CPUs and GPUs were not designed for sustained AI inference at low power. To support on-device AI, US hardware companies are integrating neural processing units specifically optimized for matrix operations, pattern recognition, and probabilistic workloads. These chips handle AI tasks more efficiently than general-purpose processors, allowing intelligence to run without draining batteries or overheating devices. This has altered how silicon budgets are allocated. Instead of pushing all performance into CPUs or GPUs, designers are redistributing transistor space toward AI acceleration. This often means sacrificing some peak performance in exchange for better efficiency and predictability. The goal is not to make devices faster in short bursts, but smarter over long periods of time. Power management has become one of the most critical design challenges. On-device AI runs even when users are not actively interacting with their devices. Background tasks like voice detection, image analysis, security monitoring, and personalization are always on. Hardware must support these workloads without creating noticeable battery drain. This has forced designers to rethink power states, scheduling, and workload prioritization at the silicon level. Battery design has evolved alongside this shift. Instead of optimizing batteries purely for screen-on time, manufacturers now design for sustained background load. This includes reserve capacity, smarter charging behavior, and tighter integration between battery management systems and AI workloads. Hardware must anticipate AI usage patterns rather than react to them. Thermal design has also changed. AI workloads generate heat differently than traditional tasks. They may not spike temperatures dramatically, but they produce steady thermal output over time. This requires new approaches to heat dissipation. US hardware firms are redesigning internal layouts, materials, and airflow to manage continuous heat rather than short bursts. Devices are becoming slightly thicker or heavier in exchange for thermal stability. Memory architecture has been heavily affected as well. On-device AI requires fast access to data and models. This has increased demand for higher memory bandwidth and more efficient caching. Hardware designers are placing memory closer to AI processors to reduce latency and power consumption. Storage systems are also being optimized to support frequent model access without excessive wear or delay. Another major shift is predictability over peak benchmarks. Traditional hardware marketing focused on maximum performance numbers. On-device AI has changed what matters internally. Hardware is now judged by how consistently it performs under mixed workloads. AI tasks must not interfere with core functions like responsiveness, connectivity, or user input. Stability has become more important than raw speed. Sensor integration has also evolved. On-device AI relies heavily on sensor data, including cameras, microphones, motion sensors, biometric readers, and environmental inputs. Hardware designers are integrating sensors more tightly with AI processing paths. This reduces latency and allows AI systems to react in real time without sending data elsewhere. Privacy considerations are now influencing hardware design directly. Processing data locally allows companies to reduce how much sensitive information leaves the device. To support this, hardware includes secure enclaves, isolated memory regions, and encrypted processing paths. Security is no longer just a software concern. It is baked into silicon and board design. Connectivity design has changed too. On-device AI reduces reliance on constant cloud access, but devices still need to sync, update, and coordinate. Hardware must balance local intelligence with efficient data transfer. Radios, antennas, and networking components are being optimized for smarter, less frequent communication rather than continuous streaming. Manufacturing decisions have also been affected. Not all components are equally capable of supporting AI workloads. Variability in chips, memory, or sensors can affect AI behavior. Hardware designers are tightening tolerances and building calibration systems to ensure consistent AI performance across production batches. Another important change is lifecycle planning. On-device AI models evolve over time. Hardware must be capable of supporting future updates without becoming obsolete too quickly. This has influenced decisions around memory capacity, storage headroom, and compute margins. Devices are being designed with longer useful lifespans in mind. This shift has also influenced product segmentation. Instead of differentiating devices purely by screen size or cosmetic features, companies increasingly differentiate by AI capability. Entry-level devices may support basic on-device AI, while higher-end models handle more complex workloads locally. Hardware tiers are now intelligence tiers. Importantly, this transformation has changed collaboration inside companies. Hardware, software, and AI teams can no longer work in isolation. AI requirements now shape hardware decisions from the earliest design stages. This tight integration has slowed some development cycles but produced more coherent products. From a business perspective, on-device AI changes cost structures. Upfront hardware costs may rise slightly, but long-term cloud expenses decline. This trade-off makes devices more expensive to design, but cheaper to operate at scale. Hardware design is now part of cost optimization strategy, not just product differentiation. On-device AI has also changed failure tolerance. When intelligence runs locally, hardware failures affect more than performance. They affect behavior. Designers are building redundancy, fallback logic, and safe modes into hardware to ensure AI systems fail gracefully rather than catastrophically. In the US, regulatory and legal pressure has reinforced this trend. Local processing simplifies compliance with data protection and AI accountability rules. Hardware that supports on-device AI makes it easier for companies to meet evolving legal standards without redesigning backend systems. The cumulative effect of these changes is profound. Devices are no longer passive endpoints. They are active participants in intelligence. Hardware is no longer designed just to execute instructions. It is designed to interpret context, anticipate needs, and respond continuously. In 2026, how on-device AI is changing hardware design in the US reflects a broader shift in how technology is built. Intelligence is moving closer to the user, and hardware is adapting to support that reality. This change is not temporary. As AI becomes ambient, always on, and deeply integrated into daily life, hardware must be designed for endurance, efficiency, and trust. The era of cloud-dependent intelligence is giving way to a hybrid model where devices think for themselves. On-device AI has turned hardware into a strategic asset again. It determines what AI can do, how reliably it works, and how much it costs to operate. In the next generation of US consumer and enterprise devices, hardware will not just support software, it will define intelligence itself.